Hello, and welcome to the Daily Space. I am your host, Beth Johnson. Pamela is off today, so I will be here solo to put science in your brain. Later in today's episode, I'm going to be joined by PSI's own David Horvath to discuss volcanism on Mars. Before we get to that, however, we have a lot of weird science to cover. Geologists and planetary scientists do a lot of different things to try to understand all the processes that shape our planet and others. From sending spacecraft to the far corners of the solar system to digging through the minerals of our planet, you never know where they will find the latest breakthroughs. And it turns out some of the most interesting results come from laboratory experiments designed to recreate the conditions of other worlds. In a new experiment published in Nature Astronomy and led by Tao-Yuen Kim, researchers studied what happens at the boundary between an ice giant's high-pressure water layer and deeper rock layer. Ice giants like Uranus and Neptune are the most commonly discovered planets in our galaxy, and they have, for a planet, fairly straightforward structures that include an outer gas layer, ice or fluid, a rocky mantle, and then a metallic core. To replicate the water-rock boundary, they combined rocks, olivine and ferropericlates, and water, and then compressed the sample in a diamond anvil. The temperatures and pressures allowed the water to draw magnesium out of the rocks in large amounts, and this indicates that fluid layers in ice giants may be rich in magnesium. This is important because magnesium-rich water is a good thermal insulator. This may explain how Uranus, which is closer to the sun than Neptune, is cooler of the two worlds. According to study co-authors Xianghong Dan Shim, this magnesium-rich water may act like a thermal blanket for the interior of the planet, allowing it to block heat from escaping. Here is to hoping we see more and more awesome lab science results as universities begin to reopen their facilities. As much as we love lab science, there really isn't anything like getting out there and exploring the sky with telescopes. The only problem is, for most things in the universe, we only get one viewing angle, and that is the random one we have from here on the surface of the Earth. This puts where we are at the whim of the universe, and while we find plenty of stuff aligned at angles varying from edge on to face forward, just like photographers inching around our subject, for some science we want a very specific viewing angle, and finding that angle requires a bit of luck, which scientists observing the still-forming star GV Tau N just happen to have. This star is still accreting matter from a large disk of gas and dust that surrounds it. From our vantage point on Earth, this system is ever so slightly tilted, and this tilt allows us to see straight along the edge of that wedge-shaped disk to the star in its center. Using the Texas spectrograph on the Gemini North Telescope in Hawaii, the team measured the flow of material along the wedge and discovered rapidly inflowing gas in the amounts predicted by star formation theories. Specifically, they found a few Earth masses of material per year flowing in. This is one of those rare and glorious instances where we can say the observations matched what we expected from theory, and it looks like we understand one more beautiful part of star formation. One of the problems with trying to sort reality from theory is that mathematically, a lot of things are possible that aren't actually real. For instance, we could turn the Earth into a black hole that could politely sit in the palm of your hand, at least for a moment, before it completely consumed you with its gravity. The issue is there aren't any situations in which the Earth is going to find itself suddenly compressed. Even if some advanced alien civilization did exist with the desire to compress the Earth into a black hole, they wouldn't, because the required energy is just, well, a lot. Basically, black holes could exist at absolutely any size. All that is required is for something to get compressed down so tiny that the escape velocity for that something, the speed that you have to go to escape its gravity, that speed just has to equal the speed of light, and boom, black hole. With sufficient energy, anyone out there could be turned into a black hole. You wouldn't survive the process, but math say it can happen. When astronomers go looking for black holes, what we find is that objects with masses between roughly 50 to 120 solar masses just aren't out there. This is because the most massive stars don't form black holes when they die. They simply explode themselves completely apart and leave behind an empty supernova remnant. We see black holes form around 3 solar masses and up, but there is a naturally occurring gap starting around 50 solar masses, and that gap could have another edge if black holes form during the death of even larger objects that are too heavy to blow themselves apart. These objects, well, we're still looking for them, but in a new paper in the Astrophysical Journal Letters by Jose Maria Esquiaga and Daniel E. Holtz, we learn that if they exist, and we have no idea if stars survive with enough mass to form them, if they exist, they could be detected during the next LIGO Virgo run as the most massive black hole binaries merging. They can also potentially be seen in the future LISA mission. Maybe. But it is neat to think that stars could form black holes with this weird distribution that starts around 3 solar masses, builds up to 50 solar masses, and then just skips ahead to 120 solar masses. We don't know if it's real, but it's a neat idea worth thinking about. After the break, we'll be back to talk about the expansion of the universe. Stay tuned. There are actually a lot of really cool theories out there involving black holes, gravity, the expansion of the universe, and a lot of really awesome ideas that make me glad that I studied planetary science, because some of these ideas seemed designed to trigger a migraine. Gravity, for instance. Every time we think we finally understand it, someone comes along and throws out an idea that just might be a better match to reality than what we have now. It all started with Newton. He watched that mythical apple fall, looked to the moon, and realized it's also falling, but just missing the Earth, and a whole lot of math later, including the entire development of calculus. Well, after a whole lot of math, he had nice sets of equations that allowed accurate predictions of both how objects would fall on Earth and how planets should orbit the sun. And for the most part, those equations matched reality. But there was a problem: Mercury. Mercury's orbit was a few seconds off, and as the years went by and technology got better, it became impossible to ignore that Mercury just didn't quite match. This discrepancy was finally explained away when Einstein's theories of relativity clarified that time and space twist to force the speed of light to always appear the same. Explaining Mercury was just one of a myriad observational pieces of evidence we have saying that relativity works. But there is always that but. Newton's theories work at lower speeds and in lower gravity environments than what Mercury experiences. Einstein's theories also have their breaking point. Specifically, they don't work at either quantum scales, and everything breaks down inside a black hole. This means we still have more to learn. When Vera Rubin discovered in the middle of the last century that the outer parts of our galaxy just don't orbit at the expected velocities, folks looked at two different explanations. The one that would go on to be most accepted is the idea of dark matter. We can explain galaxy rotations, the orbits of galaxies in clusters, and the bending of light as it travels through space by saying there is an unobserved kind of matter that we named dark matter. Literally, we explain the odd variations in orbits by adding invisible stuff to the universe. But dark matter wasn't the only theory. Many researchers have also chased additional terms to add to gravity, factors that only kick in at huge distances. Called modified Newtonian dynamics, or MOND, these theories can be made to work in all manner of situations without requiring invisible matter. For the most part, people stopped studying MOND when it became possible to measure the distribution of invisible matter by its gravitational pull on light. But some folks kept working on MOND, and in a new paper in the Astrophysical Journal Letters, researchers led by Kyu-Hyun Choi propose a new version of MOND that is able to explain, in a consistent way, both the observed motions in spiral and elliptical galaxies. This is important because these two kinds of systems have very different gravitational fields to go with their very different shapes. If this team is right, or at least on the right path, it could indicate that the universe has once again decided to follow the rules of improv and say yes and. It could be there is both an additional term to gravity and there is weird, pretty hard to detect stuff out there which we will call dark matter. It's possible, maybe, maybe. that both are true. Now, to be clear, we can explain everything we see today with just dark matter. We don't require modified gravity to solve rotation curves. We just know gravity is missing something, and this is an interesting road to follow, just in case it does allow us to find those missing pieces. Does your brain hurt yet? I know mine does. Don't worry, after the break, we're going to sit back and relax over a nice interview with Dr. Dave Horvath about Mars and his latest paper, which described possible active volcanism on the red planet. Joining me now is Dr. David Horvath, a research scientist at the Planetary Science Institute, whose most recent work has set the science community and the internet aflutter. He has published the results of research performed as a postdoc at the University of Arizona that provides evidence that Mars is still volcanically active, at least as of 50,000 years ago. Articles on this announcement have appeared everywhere, from CNN to Popular Science to even comicbook.com. Thank you for joining us, Dr. Horvath, and welcome.
Oh, thank you. Thanks for having me.
Thank you for being here. So, can you give us just a quick rundown of your research, what you found in this paper?
Yeah, so this is kind of an anomalous dark spot that's in a fairly, at least, young volcanic region, Elysium Planitia, and it just sits around this this fissure that looks like it's sourced just kind of ash and rock material deposited on the surface, and is suggestive of fairly recent volcanic activity, as recent as about 50,000 years, but definitely raises the possibility that Mars may still be volcanically active and kind of stirring below the surface.
So, how is this fissure different from the other, like, larger volcanoes that we've seen, or some of the volcanic fields that were also recently sort of analyzed?
Yeah, this is a lot of the other volcanism on Mars is lava flows, big lava flows, some coming from these fissures or building up, Elysium, the big volcanoes, Elysium Mons or Olympus Mons, or kind of the bigger Tharsis region. But this is just a really small kind of gasp of rock ash, that has just kind of emanated from this fissure. Definitely a different process, more explosive eruption. But these things may have been more prevalent. There's other evidence of some explosive eruptions. They would be really easy to kind of erode and possibly cover by later, much larger lava flows. And so we really only see this kind of one on the surface in this region.
So I know our audience is probably going to ask this, but I want to ask it of you first. How can you tell, like, from not being there, how can you tell that this is not, say, a crater?
Yeah. Topography is the big indicator that this is just kind of a flat, a flat feature region. There's a pretty prominent crater nearby, and so just based on visible, but also some topographic information, you can tell that this is not just a hole in the ground, right? This is just a material that's just blanketing the surface, covering up kind of these older lava flows.
And have we been able to determine what the rocks around here are made of?
So it's very similar to a lot of what you would expect in young volcanism, kind of a high calcium pyroxene material. And that's also consistent with some dark mantling features on the moon and Mercury. Now, a lot of young volcanism, if it hasn't been weathered down, has this kind of signature. So it's not a complete tell, but it's definitely indicative that it's kind of volcanic origin.
And what I know you kind of connected your this particular research to some of the stuff that InSight is doing. How are these two connected?
Well, InSight, only a handful of Mars quakes have really been located, and at least the two early ones that they kind of located to a specific region were from this kind of fissure system. And so, potentially, and that kind of supports this young, ongoing volcanic activity, if they're kind of detecting Mars quakes, which could be due to kind of deeper magmatic movement, in the deep subsurface. So just an extra link that, we're looking at something that's incredibly young and that Mars could still be volcanically active.
All right. Well, I have a few more questions for you, but right now we're going to take a quick break and we'll be right back. All right, I am here with Dr. David Horvath, a research scientist from the Planetary Science Institute, and we are talking about his latest research on potentially active volcanism on Mars that may still be going on. Now, I know we've tried to clarify and be very specific that this is 50,000 years ago, which to a human seems like a very long time. Can you explain to people why this is actually very important and geologically speaking is basically yesterday?
Yeah, I mean, 50,000 years is, geologically is really very recent. I think if you compressed all of Mars history into a single day, this would be that kind of the last second of that 24-hour period. So very, very recent. And, compared to a lot of the other features on Mars, which are, millions, billions of years old, this is, very, very, just in a really recent period.
So do we think that there is evidence that the volcanism may still be occurring, even as much as today, like that recently?
Not necessarily direct evidence that you do have necessarily ongoing. Of course, the Mars quakes detected by InSight could point to something happening in the deeper subsurface. But definitely raises the potential that a present day, some present day activity could occur. And of course, we've only observed Mars for 50 years or so with kind of with more recent technology. So I think we've only really looked at it in a really small window, and definitely possible that there could be active stuff that could occur in the future.
So we haven't seen any evidence of eruptions from very recently, but one of the things that this paper talks about, or at least the press release talks about, is how with InSight detecting these Mars quakes in Cerebus Fossae, there could be magma moving underground right now. So Mars may not be as sort of dead as we've been led to believe. Is that an accurate summation?
Yeah, absolutely. And there are other ways to create Mars quakes, of course, and there have been some recent work that's looked at that could be by a fluid movement. So not definitive, but definitely fits with this young volcanic story.
I feel like so much of what we're learning about Mars right now has to do with the subsurface activities. So there's been research on subsurface water. There's now research that maybe there's some subsurface magma movement. How do these come together for the thing that everybody really wants to know? Is Mars still capable of hosting life?
Yeah, I mean, and Elysium itself, from the kind of crater morphology of how these things have when these things impact the surface, how they've formed, it is indicative that you possibly have some subsurface ice. And so that kind of near surface water, and then if you have a magmatic body moving up that could create one of these young eruptions, that heat would kind of interact with that near surface ice and create kind of a potential habitable region where microbial life could live, bacterias and such, maybe things that you might find in Iceland today. So yeah, definitely this region too has that kind of component of a heat source and water that is definitely conducive to habitability.
So what is next for you on this research? What are you doing now?
Well, there are some interesting features nearby this deposit, and they may be related to maybe this activity as well, just kind of to a lesser extent. They were less convincing, which is why we really focused on this one feature. But definitely, continued InSight observations will obviously kind of help us to understand the subsurface. So kind of continued surface, but also subsurface observations are really key to kind of understanding whether or not Mars is presently active and whether it will erupt again.
And one non-science question for you: how amazing has the coverage of this been for you? It's even astounded me, some of the places your story has turned up at. So what has that been like?
Yeah, I mean, it definitely, I guess I didn't expect it to really take off like this. Yeah, I mean, it's definitely been fun doing interviews and seeing that out there. So yeah, and definitely have a lot of the PSI media people to thank for that too, because they've done such a great job. So.
Well, we are really glad that you came to talk to us too. I mean, I know we're part of PSI and we're part of that PSI media, but it is so nice that you came on our show as well when you've been on CNN.
Oh, absolutely.
So thank you.
Yeah.
Thank you so much for joining us today, and much appreciated. So good luck in your future research.
Yeah, thank you. And thanks for having me.